Hello, this is a suggested problem set. We'll call it 5.2.1. This is for people who are having some need of additional practice for evaluating definite integrals, which we see a lot when we deal with our universally useful definition of work. So, starting in at number 1, we start with a relatively simple thing, and quick reminder, this right here, this awkward S or F, is what we call an integral sign, and that evaluates at two bounds. Here we have 0 and 1. So if you think about it, what this really means is the area between 0 and 1 for dx, so that's for x, for the function 2x. So it's like, what is the area underneath the graph, so 2x would be something like this, for this part right here, from 0 to 1. So, to evaluate this, I'm going to go ahead and rewrite it, and if you're not very familiar with doing integrals, I suggest you rewrite the problems initially anyway, just to get used to writing the integral sign and setting it up. The first thing we'll do is we'll do an antiderivative of 2x, and so for us, that's just going to be, so we're going to take 2x, and so this is 2x to the 1, and we're going to raise this power by 1, and then we're going to divide by the new power. So 1 plus 1 is going to be 2. Then we're going to evaluate that at two bounds. So we have an upper and a lower. The lower is 1, the lower is 0, and the upper is 1. So let me go ahead and simplify this real quick. So the 2's cancel, and I'm left with just x squared, evaluated at 0 and 1. And then all this means is we have the upper bound, or the upper bound, minus the lower bound if you plug that in for x. So that would be 1 squared minus 0 squared. So for us, that's just going to be 1. And that is this first integral. Moving over to number 2 and changing colors, we have an integral with a negative lower bound. So I'm going to go ahead and rewrite this. So we have negative 1 to 0, the integral of x minus 2 dx. So here we're just going to take the antiderivative of each term separately. We can do that in calculus. So we're just going to do the x by itself. So this is x to the 1, so we're going to make that up to x to the 2, and then divide by that new power, so that is divided by 2. Then here for this next term, we don't have an x, so that means that it's x to the 0. So we raise that from x to the 0 to x to the 1, and that just becomes 2x to the 1 over 1. So we divide by that 1 power. And then we evaluate this at 0 and negative 1, or from 0 to negative 1, or vice versa. Technically it would be negative 1 to 0. Then I'm going to simplify this one step. So x squared times 1/2 minus, this is just 2x. And you can write it in brackets if you like. So you can say like this, and that's negative 1 and 0. So from here, we just plug this in. So it's going to be upper bound minus lower. So that's going to be 1/2 0 squared minus 2 times 0 minus. So we're doing the same thing, but we're substituting in the negative 1 instead of the 0. So that's 1/2 negative 1 squared minus 2 times negative 1. So this whole first thing is 0. On the right-hand side, we have negative, so we have negative of this whole thing, so that's 1/2 times negative 1 squared, which is just positive 1, so we have 1/2, minus, so 2 times negative 1 is negative 2, so plus 2, and so that's going to be 3/2, try that again, that'll be 5/2, and that'll be negative of that. So we can just go up and we can say that this is, I like decimals and we typically use decimals in physics, so we'll go ahead and say that this is negative 2.5. So moving on to number 3 and changing colors. Here we have a slightly lengthier integral, so we have negative 1 to 1, the integral of t squared minus 2 dt. So for the beginning, we're just going to take the antiderivative of each term. So t squared, we're going to go t to the 2 plus 1, that's 3, and then we're going to divide by that, so divide by 3, minus, again we have no x, which means it's x to the 0 right now, so we raise that to x to the 1, and we divide by 1, and then we are evaluating this from -1 to 1. So let me clean this up a little bit. We have 1/3 t cubed minus 2, I'm sorry, I wrote an x up here and it meant to be a t, minus 2t, and then we're evaluating from -1 to 1. So I'm going to go ahead and plug those in. So upper minus lower. So 1/3 times 1 cubed minus 2 times 1 minus, now the lower bound, 1/3 -1 cubed minus 2 times -1. So this simplifies, I'll just do it one at a time. So this will be 1 cubed is 1, so that will be 1/3. And then 2 times 1 is 2, so minus 2. Then for this next one, we have -1 cubed, which is -1. So we'll have negative, so this will be -1/3. And this will be -2 times -1, so plus 2. So we have a little bit of fractions going on here. I'm just going to go up to the side. So 1/3 minus 2, so that will be -5/6. Oops, not 5/6. -5/3. Then we have, in here, we have +5/3. So that would be minus that. So that means that we have, in the end, -10/3, or we can go ahead and write -3.3. We can say repeating if you guys really want to. This is a math worksheet, so why not? When in Rome. All right. Moving on to number 4, we have, rewriting it, so we have the integral from 0 to 1 of 2t minus 1 squared dt. So you can do the chain rule for this. If we want to do the chain rule, that would be fine. We could also just square this, and that would actually probably make it easier for most people. So let's go ahead and do it that way. So I'm going to go ahead and expand this square. So we have 2t, actually I want to do it up here. So we have 2t minus 1 times 2t minus 1. So now we have 2t times 2t, which is 4t squared. Then we have minus 2t minus 2t, and then plus 1. So in the end, I'll have 4t squared minus 4t plus 1 dt. Now, because I expanded that square, I can do this integral just like the others, where I do one term at a time. So this first term, I'm going to take the antiderivative, so that will be 4t. Now I'm going to take the 2, raise it 1, and then divide by the new power, which is 3. Then I'm going to move on to the next term, so I have 4t. I'm going to go from 1 up to 2, and then divide by that new power, so that's 2. And then here I have 1, and that's times, there's no x, so that's x to the 0, so I just raise that to x to the 1 over 1, and I evaluate from 0 to 1. So let me clean this up. So I have 4/3 t cubed minus 2t squared plus x. Not x, dang it, I did it again. So that is t. So plus t. Now I'm just going to evaluate it. So all of these terms included t. So I have 4/3 1 cubed minus 2 times 1 squared plus 1 minus, so all of these terms involve a t, and since my lower bound is 0, this whole thing is going to be 0. So I'm not going to go through the trouble of writing all that. So this ends up being 4/3 minus 2 plus 1. So 4/3 minus 1 is just going to be 1/3. So moving on to the next problem and changing colors. So here we start working with negative exponents. So I'm going to rewrite this. So I have the integral from 1 to 2 of 3 over x squared minus 1 dx. So I'm going to rewrite this as a negative exponent because that makes it easier for me to visualize my antiderivatives. So I'm going to rewrite this as 3 times x to the negative 2 minus 1 dx. And so now I'm going to take the antiderivative of each term. So the first term, I'll have 3x to the negative 2. So I'm going to raise that 1. And then that'll be negative 1. So I will divide by negative 1. Minus, so this is just 1. Now that's going to be x from the 0 plus 1. So I'll divide by the new power, which is 1. And then I'm going to evaluate from 1 to 2. So let me clean this up. So we have 3, and now it's negative because I'm dividing by negative 1, times x to the negative 1 minus just x. And then we're evaluating from 1 to 2. So this ends up being negative 3, and we can just go ahead and put it back in the bottom, over 2 minus 2. So that's my upper bound, minus my lower, which will be negative 3 over 1 minus 1. So I need to do this one step at a time, so that ends up being negative 1 and a half minus 2 minus, so I have negative 3 minus 1, so that's negative 4. And so this is negative 3.5 plus 4. So this is just positive 0.5 in the end. So moving on to number 6 and changing colors. So here I have a fractional exponent, which is fine. I just have to do fractions when I'm changing my exponents. So I'll rewrite this. Integral from negative 1 to 1. Oops. Integral from negative 1 to 1 of t to the 1/3, which is a cube root, minus 2 dt. So I'm just going to take the antiderivative of each term. So I have t to the 1/3, so I'm going to add 1 to that. So 1/3 plus 1 is 4/3, so I'm going to divide by 4/3. Then there's no t here, so I'm going to take this as t to the 0, raise that by 1 power over 1. And then I'm evaluating this from negative 1 to 1. So let me go ahead and clean this up. So dividing by 4/3 is the same as multiplying by 3/4. So I'll write that as 3/4 t, and then this is raised to now the 4/3 minus just 2t, and then evaluate my upper and lower bounds. So I have 3/4 times 1 to the 4/3 minus 2 times 1. So that's my upper bound, minus 3/4 t, I'm sorry, not t. We don't want t any longer. We want negative 1 raised to the 4/3 minus 2 times negative 1. So this first part should be easy. So 1 to the 4/3 is just 1. So we have 3/4. I'm actually going to go ahead and write this as a decimal. So we're going to go ahead and write that as 0.75 minus 2. So that's my upper bound, a little simplified. And here we have negative 1 to the 4/3. So technically you can do this in either order. So the cube root of negative 1 would just be negative 1. And then raised to the 4th power, since it's an even power, would be positive 1. So this ends up just being 3/4 times positive 1, which is, again, 0.75. And then here I have minus 2 times negative 1, so that would end up being plus 2. So I have 0.75 minus 2, which is 1.25, minus 2.75. So this ends up being just negative 1.5. All right, so we finished the first page of this, and now we might be skipping around a little bit because there are certain aspects of taking integrals that are not directly applicable to most of what we need for physics. So we are going to do number 7, which is just 2 fractional exponents together. So I'm going to go ahead and zoom in on this and rewrite it. So I have the integral from -1 to 0 of t to the 1/3 minus t to the 2/3 dt. So here we're just working with two different fractional exponents, so I'm going to take the antiderivative of each term. So t to the 1/3, I'm going to add 1 to that, and then divide by my new power, which is 4/3, minus, so I'm going to take my t to the 2/3, I'm going to add 1 to that, and so that's 5/3. So I'm going to divide by 5/3, and then I'm going to evaluate it from -1 to 0. So let me clean this up. This is a little ugly. So we have dividing by 4/3 is the same as multiplying by 3/4. So that's 3/4 times t to the 4/3 minus, so let's see, so dividing by 5/3 is the same as multiplying by 3/5. So minus 3/5 times t raised to the 5/3. So we're going to evaluate this from -1 to 0. So my upper limit is 0, which is great because both of these terms involve a t, so I don't need anything there. So it's just 0. Minus my lower bound, which is going to be 3/4 times -1 raised to the 4/3 minus 3/5 -1 to the 5/3. So it's a little gross looking, but we can do it. So 3/4 is the same as, so -1 raised to the 4/3. So -1 cube root is -1, raised to the 4th is +1. So this just ends up being 3/4, which I'm going to go ahead and write as 0.75. Actually, don't forget this is all negative at the end. Minus, so here we have -1, cube root again is -1, raised to the 5th, since it's an odd power, is also -1. So we have -1 times 3/5. And so 3/5 I'm going to write as a decimal. 3/5 as a decimal is 0.6, so we will be plus 0.6. And so we take the negative of this whole thing. So 0.75 plus 0.6 is negative 1.35. Now, as I said, we're going to be skipping around a little bit. We do not need to do number 8. So we will not be doing number 8. We do not need to know absolute value integration right now. We do, however, need to know some trig integration. So, real quick, just a reminder, if you take the derivative of sine of x, that is equal to cosine of x. And the derivative of cosine of x is negative sine of x. So, just keep these in mind when we're talking about antiderivatives of sine and cosine. So I'm going to go ahead and rewrite this. So I have the integral from 0 to pi of 1 plus sine x and then dx. So just like before, even though there's a trig function, I can take the antiderivative of each term by itself. So the antiderivative of 1, since there's no x there, is going to be x to the 0 plus 1 over my new power of 1. Plus, so the antiderivative of sine. So this is something you're just going to have to remember. So if the derivative of cosine is negative sine, that would mean that the derivative of negative cosine would be positive sine. So that means my antiderivative of sine is actually negative cosine x. So unlike the polynomial terms, when we do trig functions, you kind of need to know how to move between sine and cosine of x. So we're going to evaluate this from 0 to pi, and that leaves us with, so if we clean this up, that's just x minus cosine of x, evaluated from 0 to pi. And so that's going to be my upper limit, which is pi minus cosine of pi, minus pi, I'm sorry, not pi, so minus our lower limit, which is going to be 0 minus cosine of 0. So cosine of pi is -1. So I have pi plus 1 in my first grouping, my upper bound, minus 0 minus cosine of 0. So cosine of 0 is +1. So that means this is minus a -1. So I end up with just pi plus 2, which you can leave it as for right now. If you really want to go through, you could say 5.14 if you really, really, really wanted that decimal value. All right, so let's skip on to the next one. So here we have another trig function, but we don't really need to know this one. I will say that it relates to something that's not sine or cosine, so we're just going to leave it as that for now. Same with number 11. So let's go on to number 12. So number 12 is a kind of a word problem. It says, what is the exact area of the region between this function and the x-axis over the interval 0 to 1? So this is asking us what is the integral of, or from 0 to 1 of x minus x squared dx. So this whole phrasing is asking us for the integral for this interval. So we're just going to do what we know how to do, which is to take the antiderivative of each term separately. So we have x to the 1, raise that by 1 power, now we're dividing by 2, minus x to the 2, raise that 1 power, so now we divide by 3, and we are evaluating this from 0 to 1. So let's clean this up. We have 1/2 x squared minus 1/3 x cubed, evaluated from 0 to 1. So I end up with 1/2 times 1 squared minus 1/3 times 1 cubed is my upper bound, minus, well, both of these have x in them, so ends up being 0. So in the end, I have 1/2 times 1 minus 1/3. So if you do this as a decimal, you end up with 0.5 minus 0.33333333. You could do it with fractions, up to you. If you do it with fractions, you would end up with, let's see, that would be 3/6 minus, so that's 1/6. That's fine. If you do the decimals, you would end up with 0.1666666 forever. So there you go. And moving on. So we have, need to zoom out. What is the exact area of the region between y equals cosine of x and the x-axis over the interval 0 to pi over 2? So let me change colors again. So here we are again looking for the integral, I guess we'll write it right here in the middle. The integral from, so this is my interval, so 0 to pi over 2 of this function, so that's cosine of x dx. So I'm just going to take the integral of cosine of x. Well, that's actually something really easy because the derivative of sine of x is cosine of x. So the antiderivative of cosine of x must be sine of x. And then I'm just going to evaluate this from 0 to pi over 2. So my upper bound minus my lower. So I have sine of pi over 2 minus sine of 0. Well, the sine of 0 is 0, and the sine of pi over 2 is 1. So my answer ends up just being 1. And so this is really as far as we need to go for this worksheet. This right here, if you are interested in a little bit of a puzzle concerning integrals, you can go ahead and do numbers 14 through 19 that involves this kind of information. And then the same is true for numbers 20 through 26. So if you really want an interesting challenge, go ahead and do these. If you have questions about them, please see me in person or send me an email.